Alright, I think we can start today's webinar now. First of all, a warm welcome to yet another one of Diabetics' webinars. My name is Niels Verdijk and I will be your host today. Apart from being your host, I'm also one of the customer support engineers at Diabetics. So basically that means if you have any technical questions or you do a project with us, you'll for sure get in contact with me again. But that's enough about myself. I don't want to give a webinar purely about myself. You came to follow the title that you see here, how to design a liquid cooling solution for a double-sided power inverter. For today's webinar, I've split up the content in the following points. So first, of course, I'll give a bit of an introduction to both the problem and the application later on. Then we'll move on to the design methodology for thermal components. So how should you tackle such a problem? How concept generation fits into that, giving you insight into traditional design versus custom designs. And then we'll apply all that learning to then a double-sided power inverter. Afterwards, we can move on to the Q&A session. So if you have any questions, feel free to put them in the chat box. Our moderators are following along, and any interesting questions that the moderators will find, they will let me know. So those I will cover in the questions side. And lastly, I hope that during the Christmas and New Year period, you'll have some time to play around with the software. Hopefully I will have convinced you. And towards the end, I will give you some information on where you can discover ColdStream for your own. As ever, I will try to fit this all in 30 minutes, so hopefully we will succeed again. Okay, that's everything that I wanted to cover here, so let us move on. Why should you care? Why should this webinar be of interest to you? As you know, or with power inverter designing, you usually focus first on the electronics components, making sure that everything fits on the PCB and everything works properly. And then towards the end, the thermal problem needs to be tackled, making sure that the components don't overheat, etc. And usually that's treated towards the end, as I've mentioned. But as you will have noticed over the years, the power output of such components, of all the chips, etc., has increased, making it more and more challenging to meet all the thermal requirements. So postponing that step, the thermal design, towards the end becomes more and more challenging. And that's where we, Diabetics, we want to focus on. Our sole purpose is to give designers like yourself access to smart algorithms. And these smart algorithms can help you throughout the entire design process by giving you insights into whether or not the cooling requirements will be met, or basically finalizing the final design. You see on the top right, ANSYS and Hexagon, two of the very big names within the CFD world. Both of them have acknowledged the strength of our software, have reached out to us, and as of recent, we made them our technology partners. Okay, what I mentioned, smart algorithms, that's quite vague. To put it more into context, or to put it more into perspective, I will first cover what the conventional way of working is, which I'm sure you're all very familiar with, where you start with your layout of your PCB, all the different heat sources, etc., and then below it or above it, depending on your point of view, you have then a cooling plate that needs to cool down all of those heat sources. That usually starts empty, but you then create a first CAD model, be it based on past experience, or you saw something interesting via LinkedIn or something. You draw the design, you run a CFD simulation or the physical experiments, you analyze the results and make modifications. You typically loop through this a couple of times until you get a solution. The amount of loops that you can do is of course dependent on how much time you can spend on it. with generative design, that process is completely different, as you can see from the slide deck. So rather than tackling thermal problem towards the end, you can use ColdStream as a concept generator. So we start from the same the same input. So it's with your heat sources and a heatsink. But by using the concept generator, you don't have to tackle it towards the end. You can basically, if you have a proposal for PCB layout, you can put it to ColdStream. You'll get very quick feedback whether or not these thermal requirements will be easily met or not, and make modifications if needed. So that's the concept generation stage, where either ColdStream will generate concepts for you, or if you have a design that you want to test, you can of course also simulate it using ColdStream. Okay, so that's the concept generator stage, and then you can continue using one of those concepts, be it one from ColdStream or your own, to make then a mature and final product, the optimal solution for your input. So by giving you access to all of those different steps, you basically tackle the thermal problem much earlier on, making sure that that your final product will meet the thermal requirements, or at least make it much easier to find a feasible solution. The concept generation stage. If you let ColdStream design the concepts for you in a matter of hours, you can get thousands of different designs, giving you great insight into what design change affects the performance. So as you can see here, I'll cover it more in detail in the demonstration portion of the webinar. But you'll get a great number of different designs with an overview of how the performance is affected. I've noted down here a correlation-based estimation. That's the fastest mode on ColdStream, but more on that later on. How can you tackle thermal problems, or how can you tackle the designing of the heatsinks? I've listed 3 options. I'll start from the left and then move to the right. So on the left, you have something called parametric optimization, where you a priori describe a given design philosophy, be it pins, fins, gyroids, dimples, you name it, usually more conventional cooling solutions. And for each of those cooling solutions, you find a set of parameters that basically describes your entire heatsink. I've chosen here the example of a pin. For a pin, you can describe the diameter of your pin, the height of the pin, the spacing between the pins, both in X and Y. And that limited amount of parameters basically describes your entire pin heatsink. Parametric optimization is a very fast mode, but of course, your final design is limited to the design philosophy that you select a priori. If you select pins, you will get pins. You won't get something very organic looking, for example. You're stuck with the design philosophy that you chose a priori. Then you can go to shape optimization. Shape optimization allows for more freedom in the final design. So with shape optimization, you basically give an initial shape, initial design, and then the optimizer has complete freedom to move the edges of the design around. For example, here I've drawn a blob. What the optimizer can potentially do is straighten this cavity out to make a nice convex design rather than a concave design. So the final output is not something, or mustn't necessarily be something conventional. It can be something organic. But the only limitation is your final design is very much dependent on your initial design. There are some smart things that you can do with seeding, for example, to generate cavities and new structures, but it's already quite advanced. Then we can move on to how ColdStream tackles the problem, and that's through generative design. So the entire design space is basically split or subdivided into small elements, and you can either start from scratch or you can already give it some initial push in the right direction. But ColdStream has this complete flexibility to choose whether or not it wants to fill one of those elements with material or leave it as a fluid. For example, here you can choose to fill those 4 elements with material, or this blob of material with fluids, for example, with solids, for example. And by using this optimization strategy, the final outcome is again can be something very organic, something very non-human, without the penalty of your initial design being the limiting factor. What does it look like? So here I have an IGBT cold plate. So on the top you have your heat sources, and on the bottom your heat sink. And in this video, you will see what ColdStream does in the background. So in the beginning, it's mainly adding and removing structures and a bit of reshaping, while towards the end, and when it converges to the final solution, the number of structures remains the same, and it's then mainly reshaping those structures until it gets to a final solution, like you can see here. You might think to yourself, you need a PhD for it. Not at all. On the ColdStream, it took great strides into automating all of basically the repetitive stuff. The only things that you have to do as a user is to follow basically four or 5 steps, depending on if you include downloading results as a step. In the first step, you have to upload a geometry. ColdStream itself is not a CAD software, so you prepare that geometry in your own CAD environment, be it NX, Autodesk Inventor, doesn't really matter. As long as it can export your step, it's fine. Next, you set the solids and the fluids. Is it copper that's used or aluminum? Is it air-cooled, liquid-cooled? And if liquid-cooled, is it water glycol, pure water, something else? That's something that you specify in the second step. In the third step, you define your boundary conditions. Is it a fan or a pump that drives the flow, or is it natural convection? What does the heat load look like? How much heat do my chips generate, etc. That's something that you specify in this step. And then for the next step, the fourth step, that's a bit of a new one, especially compared to more conventional CFD software. You have to define a design domain. So basically, that dictates the volume where ColdStream is allowed to modify the geometry, where it can add and remove structures and reshape those structures. And you have to let ColdStream know what to optimize for, be it heat exchange efficiency maximization, weight minimization, pressure drop constraint. ColdStream has 20+ targets that you can mix and match however you see fit. And that's basically it. So once you've gone through all those 4 steps, ColdStream will take over, be it in the concept generator stage or the mature product stage. And once ColdStream is ready, you can then download the results in step file format. Something very important, topology optimization in general, it has been used in academics for quite some time, but it also needs to be manufacturable. As one of the inputs, ColdStream requests that for each design domain that you upload, you have to let ColdStream know what kind of structures you can expect, how it will be manufactured. Here are 4 of the most commonly used manufacturing techniques: CNC milling, die casting, 3D printing, and sheet metal forming. And for each of those techniques, you have full control over the settings that govern the technique. For example, with CNC milling, you have control over the minimal channel width, so basically the milling tool size, as well as the depth of your milling operation, where you always get 2-dimensional structures. While with die casting, you have control over the minimal and maximal structure width, as well as the release angle to get it out of the mold. With 3D printing, you have that's the most freedom, of course, but quite expensive to make, especially in large volumes. Where you have control over the printing resolution, overhang angle, unsupported lengths, both the bridge and cantilever, etc. And this very much ensures, that whatever ColdStream outputs will meet your manufacturing capabilities or will meet your manufacturing constraints. Okay, that's basically all the input. If you have a few questions, I will cover everything in more detail in the demo session. That will make everything more clear, should there be any unanswered questions. Let's now apply this knowledge to a double-sided power inverter, where in this slide I summarized all the input. So we'll mainly focus on aluminum, being it's a very cheap material and still highly conductive. In total, our chips produce just over 4 kilowatts of energy, and I want to maximize heat exchange efficiency as well as maximize thermal uniformity. To make sure that the pumping power doesn't rise to infinitely high, we put a pressure loss constraint of 6 kilopascal, and we'll be using 3D printing with the printing resolution of 5 millimeters as a manufacturing technique. I will now jump to ColdStream to give you basically the live session. Where is ColdStream? There it is. Yes, you can still see my screen. Perfect. So this is ColdStream, or at least the main landing page after you log on to software, and that's the project overview. As the name implies, keeps all of your projects in all of your applications in organized folders. For this one, I will move to this project folder. Yes, and inside of your project folder, that's then all the cases, all of the engineering problems that you want to solve. ColdStream supports 3 types of cases. Simulation, that's just a regular CFD simulation, as you know it from other software. So if you have a design that you want to know the performance of, you can simulate easily in ColdStream. And then we have what we call standard design. That's basically the concept generator. And then we have custom design. That's to get to extract the maximum out of it. That's the thermal topology optimization, where you can get then very organic, very custom designs to your problem. Okay, I will first cover the concept generator stage, because that's of course early on in the design phase. So if you upload a geometry, or if you create a case, in ColdStream, it will first ask you to upload a geometry. I will skip that part and go straight to a case that already has a geometry, and that looks something like this. So for our double-sided power inverter, we have 90 chips in total, 45 on the top, 45 on the bottom. They are placed on copper heat spreaders to help spread out the heat to our heatsink in the middle. Those copper heat spreaders sandwich a cover and housing, basically purely to contain the coolant. We then have, of course, our coolant with a single inlet on the right and an outlet on the left. And in this case, we have a design domain in the middle where we allow ColdStream to modify the geometry. And the only thing left then for ColdStream to do is click on each of the entities and fill in the information. Starting with the copper heat spreaders, ColdStream will ask you, is it a solid or a fluid? In this case, of course, it is a solid. And we can then let ColdStream know out of what material it is made. If it's, for example, aluminum 6061, you can easily search for it and then assign the proper material properties. Or if you have custom material properties, you can easily create them as well in ColdStream. And it can be anisotropic if you so desire. For our case, it's pure copper, and that's sufficient. Everything below is optional, like a volumetric heat source. If it rotates, for example, all of that is optional. Then we have our chips. We could have taken the chips with us as volumetric heat sources, but we simplified it a bit for for our sake and just assumed it to be a boundary condition. Where again, from the drop down, you select the type of boundary condition you want to impose. You want to fix the temperature, you want to fix the heat input. That's entirely up to you what you want to do there. The heat as well is by far the most popular option. where you can then specify how much heat, so in total, just over 4 kilowatts of energy is produced by all 90 chips combined. I'll come back to those targets later on. That's something that you then repeat for the cover, so solid made of aluminum, and for the housing, again, a solid made out of aluminum. And for our fluid, now of course it's of type fluid, not a solid. You again specify out of what material, what coolant will be used, be it air or water, glycol, temperature dependent or temperature independent. Again, that's entirely up to you what you want to model there. And everything else is optional, like two-phase boiling if you want to enable that effect, buoyancy, so that's all optional. Then for our inlets, we can have a different couple of options. Either want to fix the flow that comes in, or you can fix the pressure at the inlet, or you can use a pump or a fan, where then ColdStream will ask you to provide the performance curve of that pump and fan. Here I chose for the fixed flow rate inlet, where I specify a given flow rate, given volumetric flow rate, and an inlet temperature of 40 degrees Celsius. And for our outlets, again, we have a couple of options, but the pressure outlet is the most common. You can also use a pump or a fan at the outlet if you want to have the sucking effect rather than the blowing effect. But again, of course, that's very much dependent on how your components are oriented. Okay, so that's solids, fluids, boundary conditions. We then can move on to the design domain. As I mentioned, the design domain dictates where ColdStream is allowed to modify the geometry. Here with the concept generator stage, you can dictate what kind of cooling solutions ColdStream can consider. You can consider pins, fins, and if so, how can those pins and fins be manufactured? For example, for this case, fins will most likely pins will allow for more dispersion over the in the plane. So I will deselect all the fin options, and I only want to consider, for example, die-casted pins. Yes, I can do so. And lastly, after that ColdStream know out of what material my pins will be generated. So now ColdStream will then optimize how many pins do I need, etc. The height and etc. Okay, so it's solids, fluids, boundary conditions, and the design domain. The last thing we have to let ColdStream know is what to optimize for, and that's where the targets come in. So here I have 1 target on my inlet and 2 targets on my heat producing component, my chips. Starting with the inlets, as I mentioned in the slide deck earlier, we want to constrain the pressure drop by 26 kilopascal. So here I let ColdStream know whatever pins that ColdStream defines, my pressure drop between in and out can never exceed 6 kilopascal. It can be lower, it can never be higher. And then we have our heat producing chips. Here, of course, we want to optimize the thermal performance, where I put 2 objectives. First of all, I want to minimize the temperature of all those components, so basically maximize heat exchange efficiency. And secondly, I want to maximize motor uniformity by minimizing the variance over all 90 chips combined. And that's it. Once all of that information has been filled in, we can then submit the case and ColdStream will take over. Luckily, you don't have to wait for it, so we can jump straight into the results, where you have a couple of options on what mode you want to go with. If you submit ColdStream on a correlation-based mode, it can basically get 1,000 different designs in an hour, and that's not an exaggeration. So that's a very fast mode, giving you quick feedback. That's more, of course, in the early stages of the design cycle. What you can also do is use ColdStream for full CFD backed, where for every design iteration, ColdStream will do a full CFD simulation. More accurate, but it will take a bit longer to run. And for every case, for every concept generator case, if you move to the design evolution tab, you can then see an overview of all the different designs that ColdStream attempted and the performance. So the overall design performance graph will give you on the x-axis the iteration counter, the design counter, and the y-axis the performance value, basically your objective function. And seeing as it's an optimization, the lower the value, the better. Where the dots can either be of 3 colors. If it's red, it means it's infeasible. For example, my pressure drop constraint is not met. If it's blue, it means it's feasible, but at that point, it's not the best one. And if it's green, it means at this point, it's the best design. So the first iteration is feasible. It will always be green, and it will only turn green again if it improves upon the previous green design. So in this case, design 23 is my best design. And if you scroll down, you can then see what's ColdStream did. I have to be honest here, for this case, I used 2 design domains. So the design domain that you saw earlier, I basically split it in half and allowed ColdStream more flexibility over the height. The only reason why I did it is for the optimization. I use 3D printing, so by splitting the design domain, I have a bit of variation over the height. But in the bottom design region, it tried 500 pins with these dimensions, and in the top region, it tried 200 pins, or the most optimal solution is 200 pins with these dimensions in mind. And if you scroll down even further, you basically then see your individual targets, so your pressure drop throughout all the designs, your temperature variance, so your uniformity of all the different designs, and the temperature minimization on all the different designs. So these graphs, especially individually, will give you a great insight into whether or not your performance requirements are already met, or how far you still are from those requirements. Okay, it looks like we're already close to the 30-minute mark, so I will speed up a bit. Now that I have this design, let's say my temperature minimization objective, that's almost perfect. My temperature variance minimization, that can still be improved. What I can now do is use this initial design to help ColdStream point already in the right direction, and further optimizing using then a custom design. So what I did for this case is I downloaded the results of the 23rd iteration in step file format, and I uploaded that to a custom design where I have a few options. So if I go to this case, the geometrical input for a custom design is identical to a standard design. So all of the regions that you see here, your chips, complete spares, cover, housing, fluid, design domain, and inlet and outlet, they're all the same as you saw with the standard design case. The only change is the input for the design domain. So in the design domain, I can now let ColdStream start from initial design. This basically helps ColdStream point in the right direction and will speed up the optimization process, where I have control over what ColdStream needs to do with that initial design. If I chose the only remove option, what ColdStream then is allowed to do is basically only remove certain pins. For example, pin at X position 10 and Y position 12, for example, and just saying something, ColdStream can choose to remove that pin or keep it. So that's the only remove option. ColdStream will never add additional material to the geometry that you upload. The only add option, that's the complementary mode. So the only add option, the pins that I've uploaded as initial design are fixed. ColdStream cannot touch it. ColdStream can only add material in between the pins. For example, you can combine 2 pins to make a small fin, or you can combine a bunch of pins to make a big blob of material if it decides to do so. And that's then available in the only add option. And then we have the add and remove option, and that's a combination of the two, of course, where ColdStream has the complete flexibility to do whatever it wants with those designs. Of course, I'll let ColdStream know what type of manufacturing technique I want to use, 3D printing, with a printing resolution of 5 millimeters. And again, I will use aluminum as a manufacturing material. Everything else remains exactly the same. And in the interest of time, I will jump straight into the results. If you only look at the add option, I will show the solid structures that ColdStream added. So the pins themselves, you will see they're all still present, and it's added material in between the pins to basically create bigger structures out of it. If you have a look at the negative, our remaining fluid, we will then see what ColdStream did. So it's made a bit of a spaghetti, a bit more of a spaghetti in between those solid structures. So this is an example of an only add case. If we then move on to an only remove case, I will first show the solid structures. So here, the spacing between the pins is as is. ColdStream couldn't touch it, but as you can see, it took away chunks of material or chunks of those pins at certain positions. And if you have a look at the negative, at our fluid, then in this case it's not as clear. The design is more clear, but it's very easy to see why ColdStream removed material at certain positions. Towards the inlet here, the coolant is still cold, while towards the end the coolant has heated up a bit. So for the thermal uniformity target, that's why it creates more contact area at those stages. And then the pure initialization, where ColdStream can add and remove material. That's of course that's something that I will show right now. If I load that in. Ooh, I see that we are already over time. I think you get the idea. I will move on to my presentation then. I'm really sorry about this, but all of these results will be made available on our viewer account. So questions, that's something I'll have to skip, unfortunately. If you want to try ColdStream for your own, during Christmas and New Year, feel free to request access to it. Or if you want to know more about the software, feel free to email to info@diabetics.com or ring this number. Thank you all for your time. I hope the 2 or 3 minutes extra wasn't too bad. And I wish you all a very pleasant Christmas and New Year period. Hope to see you later. Bye bye.